Hey everybody, this is Dr. Wood, and we are starting Lecture 3 for Epidemiology and Biostatistics. We're talking confidence intervals today. Some of the things we'll talk about is how we're going to be applying confidence intervals to a specific proportion, and then also look at how confidence intervals may apply to things like survival data. I hope your survival data at the end of this class will be 100%, but again, who's to say? So first starting out, let's talk about the confidence interval of a proportion. So if you recall, when we kind of define what a confidence interval is basically we're trying to take a set of sample data, which is very specific to that group of people that you're looking at, and trying to make more general conclusions about the population from which that sample was taken, essentially, right? And so again, we use those confidence intervals, usually with an upper and a lower range. It could be a fraction, it could be a proportion, whatever the case may be. And again, it's trying to give us an idea of if we were to apply this back to the general population, for whatever the group we're looking at, the actual true mean of that population would be somewhere within that range there. And ideally, we'd like to get as small of a confidence interval as possible. It'd be nice if we could just get one number and have no range whatsoever, but because we can't measure the entire population, we'll never be able to do that. So we're going to look at some ways we can actually get the smallest CI that we can get. Keep in mind, the calculation is pretty complex, and we are not going to be doing that. Not going to be doing that. Again, I don't know how to do it, and there's a lot of methods that are out there. So what's important, though, is that interpretation of the confidence interval and how we can apply that to our understanding of the medical literature. So oftentimes when you're reading articles in a journal, you're going to find that they do require the use of the CI. And actually what you're going to find is that a lot of people, they just look at the p-value and they say, oh, okay, the p-value is less than 0.05. This must be interesting results or must be good, quote unquote. However, the confidence interval tends to tell you a lot more about what's going on with the results of a study than any p-value ever can. Now, keep in mind that, they may phrase it in a way such as saying that we are 99% confident that the true value of our parameter is in our confidence interval, right? Or often they'll probably say something like, okay, well, there's a 95% chance that this confidence interval contains the population value. And if you recall, there's a lot of different ways you can modify the width of that confidence interval, such as how confident you want to be with it, whether you're 99% confident or just 95% confident, or also how many people you're actually looking at, whether you had, say, 12 people or you had, say, 1,000 people. So what specifically is going to have an effect on the width of that confidence interval? So when sample size is probably one of the biggest things, the largest the sample size, the smaller it's going to be, because we can be more certain because our numbers are closer to that of the whole population. However, getting your sample size up is frequently difficult and or expensive, and so that could be a major barrier to the results of your study. The size of the standard deviation there is also important. You're going to find that the more standard deviation you have, or the more variability in the data there are, basically the confidence interval is going to get bigger because you're kind of less certain about what the actual values are going to be of that whole population, since your data was so variable. And then the confidence interval that you want. And so this is the one thing that researchers would have a direct influence on in a lot of cases, is how sure you want to be. Do you want to be 95% sure, 90%? Obviously, the higher the degree of confidence, the larger the confidence interval has to be. So if you want to be 99% sure, you have to give yourself more wiggle room to make sure that the mean of the population really fits within that range there, right? So let's start off by looking at an uplifting topic. I'm very sorry about this. So let's look at deaths of premature babies. So there was a study done back in 1993, and basically it's a retrospective study, and they were looking at premature babies born between, say, 22 weeks and 25 weeks gestation. Just for reference, 38 to 42 roughly is a full-term birth. 22 to 25 weeks is very, very premature, and death in this population is fairly high, as it turns out. So anyway, so they were looking at just babies that were born to this one particular hospital during a 3-year period. And they were finding that of 29 infants who were born at 22 weeks, none survived up to 6 months. And then of 39 infants born at 25 weeks gestation, 31 survived to at least 6 months. And so basically the data was presented without any confidence intervals. And so you're going to find that it's kind of hard to take a whole lot of conclusions out of just the results unless you have some sort of confidence interval to compare these two together. And so, as we mentioned, confidence interval should be calculated when the sample is representative of the larger population. So, especially if we're trying to make inferences about that population, you need to have some sort of idea of, how that's going to apply back to that larger population. So, say how representative is the sample of babies born at 22 weeks and babies born at 25 weeks gestation, right? So, and again, when looking at the numbers here, so out of the 29 born at 22 weeks, 0% survival rate. Out of the 39 born at 25 weeks, there's roughly 80% survival rate. So what kind of confidence intervals do you think there would be if you were to, say, extrapolate it from that N of 29 and 39 out to the larger population of babies born at those respective gestational ages? So for the babies born at 22 weeks, you would find, if they were to calculate it out, this is the 95% confidence interval ranges anywhere from 0 to 11.9%. If you recall, you can't really have a negative value in this case here because you can't really have a negative birth. However, if you were, say, maybe doing the difference between two values or something like that, you could have a confidence interval that ranges into the negatives here. But for our purposes, for this case, you can't have a negative birth, right? Then for the infants born at 25 weeks, the range was anywhere between 64 to 91% survival, right? So they're trying to say is in that group that was born at 25 weeks, the actual population mean of babies born at 25 weeks, if you were to measure it across, say, the country, should be somewhere between 64 and 91%, right? They're 95% sure somewhere within that range there, okay? Let's take another example. Let's say we're going to go ahead and poll 100 randomly selected voters before an election there, and then 33 said they would vote for your candidate. I'm not going to say which candidate. I don't care which candidate, but let's just say 33 of them said they were going to vote for your candidate. And you wanted to find out, like, okay, well, how many of these people would actually vote for my candidate if I extrapolated this out to the whole population that you were looking at, right? And so two things you have to look at is one, is your sample representative of the population of voters, right? So again, if you were, say, looking for, say, the governor of Florida, if you only went into very rural areas, are those voters representative of the state at large versus, say, if you went strictly into downtown Orlando? Would that be representative of the population at large, right? If you think about the premature infants case there, are the babies born at that hospital representative of babies born elsewhere that are premature, right? So again, how representative are they? Because that can influence your results there. And then another thing could be the sampling errors there. So, looking at it, is your sample containing, say, a smaller or a larger fraction of people voting for your candidate than does the overall population? And that goes back to sort of how representative your sample is of the entire population. So, again, the best thing you can do is try to maybe calculate that range of values that would bracket out that whole population there, right? So again, assuming that we had 33 people out of 100 that said they would vote for our candidate, if we get the 95% confidence interval there, it would range anywhere between, say, 24% all the way up to 42%. So we said, okay, well, we think if we extrapolated this out to our population in question, that we get probably between 24 to 42% of the vote. We're 95% sure we would at least get that much of the vote. So what are some assumptions we're going to be using when we're looking at confidence intervals of a proportion? One is that it needs to be a representative sample of the population, right? You can't just skew and look towards just one group of people and have that expect to be generalizable to the entire group if that's not the case there. As I mentioned in the baby example we were looking at, if they were somehow selected to be sicker, if maybe they were in a hospital where they only receive sicker mothers potentially, or if there's something where they were selecting out for those babies, they may not be representative of other premature babies born elsewhere. Or in the case of the voter example, if the sample really wasn't random. So as an example, there was a poll that was done in 1936 of Roosevelt versus Landon, and the pollsters, they were trying to get an idea of who was going to be voting for who, and they actually used phone books and auto registrations. All sounds well and good, but back in the day, if you had a phone and you had a car, you were probably pretty well off compared to people who did not have phones or cars. And so you were looking at more wealthy individuals, and that may not be very representative of the group at large who are going to be voting for your candidate potentially, right? So there's some errors there that can lead you to make incorrect conclusions. Another assumption you should be making is that the observations are independent, meaning that you're not measuring the same person twice, meaning you're not measuring people who have maybe influence on the other that could lead to some incorrect conclusions. In the baby example, for instance, you wouldn't want to look at twins because they would share a similar environment and similar genetics. And so that may predispose, if one died, maybe it would predispose the other to dying as well. And so that would not be giving me a very good idea of what the greater population would look like. If you were looking at the voter example there, if pollsters were questioning husband and wife, that may influence one thing or the other. Maybe they would incorrectly assume that the wife would vote the same as the husband, vice versa. Or maybe if they asked the same person more than once, again, those would not be considered independent observations and would not be considered valid when you're trying to extrapolate out to the whole population. So another assumption should be that the data is actually accurate, right? So you have to make sure that the data is calculated correctly or tabulated correctly. In the infant example, death is fairly unambiguous. You're either alive or you're not, and so that's pretty clear. However, in the election example, oftentimes you can find the results can be skewed based on how you actually ask the question, right? You can say, okay, well, if only idiots vote for the opponent, then surely who are you going to be voting for? Things like that can really skew the results one way or the other. And so that may lead you to have inaccurate data and inaccurate conclusions. So when looking at this, what does the 95% confidence interval really mean? Again, the true value of the population, the true mean value, either lies within the 95% that you came up with or it doesn't, right? And again, you're 95% sure, which means that in 5% of the time or 1 in 20 times, you're going to be wrong, right? That's just kind of the natural assumption you're making when you say you're 95% sure about something. And so if you imagine here, you ran the same experiment with the same data over and over and over again 20 times, and look at this, 19 out of the times, the true population value is going to fall within that confidence interval, right? The one time you could be wrong there. And again, that's part of the errors we'll talk about. We talk about type 1, type 2 errors, etc. That'll come up again. But again, that's basically what we're saying is that, there could be a 5% chance that the actual population mean is not within this range. But again, chances are that it is, 95% sure. So some of the lingo you're going to run into when dealing with confidence intervals. So confidence interval versus the confidence limits. Basically, the limits is just going to be the upper and the lower range. The confidence interval will extend the entire range, right? So it's kind of the difference there. The estimate, as we mentioned, is what we're calculating out. And again, we're estimating what the actual true value of the population is. Since we can't know what that is, it'll always remain an estimate. Even if we're quite sure that the true population value falls within this range, it's still just an estimate. And then, as we mentioned with confidence levels, 95%, there's nothing special. It's kind of just an arbitrary sort of historical thing we've always done. But again, if you wanted to be more confident, you could do that, right? That's depending on where your study's going to go. Usually people don't go less confident because then at that point, you're like, well, how good are your results at that point? I'm 50% sure that the true value lies within this range. It's like, well, you're only, it's a flip of a coin. That doesn't really tell me a whole lot. But if you're 95% sure or more, that's pretty good, I think, at that point. And here's the same experiment done with 3 different confidence intervals here, 90%, 95, and 99%. Remember that basically telling the same thing, the same mean popped up every time. But in order to be more sure, you have to widen out your confidence interval. You have to give yourself more wiggle room to make sure that population mean actually falls within that range, right? Here you're saying 10% of the time you can be wrong, so it's okay if it falls outside of that range because I'm not quite as sure. Versus if I'm 99% sure, only one time out of 100 should the actual mean of the population fall outside of this value there, right? So you're giving yourself more room so that way you can be more sure of your results. Also note here, if we were to change the n of our study, so we're to have the same results, but we had it with a larger n, notice that it gets smaller and smaller the more people you include, because again, at that point, it's more representative of the entire population that you're concerned with, and so you're going to find your confidence intervals will also get more and more narrow. So it's always beneficial to include more people in your study, but oftentimes that can be difficult. It's either a disease state that's rare to find, or it can be expensive to get people enrolled, or lots of different reasons why the n may be very small. Sometimes you'll find that you can have an asymmetrical confidence interval. That's totally fine. It just depends on the case there. If you remember with the infant mortality one, notice the confidence interval went from 0 to like 11.9 or something like that. That was asymmetrical because, again, you hit the bottom floor there. In this case here, you'd hit the top floor of 100%. You couldn't go any higher than that in the case there. So it's okay if it's asymmetrical, but just know that it happens occasionally. Most of the time, it tends to be pretty centered around where the actual mean was for that value. So let's flip sides here a little bit and talk about confidence interval of survival data. So why do we care about survival data? Well, most of you probably went into medicine to try to keep your patients alive. And so by looking at this, we can see if the interventions that we're taking in our patients are actually doing anything to have them living for longer. Now, you're going to find that survival data, quote unquote, is going to be a little misleading. This can really apply to anything that happens once, right? Death is used most frequently because that is a kind of the very typical thing you think of that only happens once, right? Most people die only once, unless you're James Bond. But otherwise, this could be used for anything that happens just one time. So for instance, getting chicken pox, right? One time and you're kind of done at that point, okay? So it can be used for anything, positive or negative, but death is typically the one thing that we will tend to use most frequently in these cases here, okay? Other things you have to know, the survival time of each subject, you got to know that sort of thing there. Or if patients fall out when they get censored, we'll talk about what that means in a second, that needs to be known as well, right? So the timing that people have before they hit an event needs to be known, and it doesn't really matter as long as it's a one-time event. So when we say censored survival data, that basically means where people kind of get taken out of the calculations for one reason or another. Maybe patients kind of fall out because they don't want to follow up anymore. Maybe they move. Maybe they survive past the end of the study period. If at any point they don't get included in the final results, that's called censored survival data. It's important to make note of people that are censored because if researchers didn't make note of it, it would seem kind of fishy if data just mysteriously stopped. Like, if you had 100 patients you enrolled throughout the study, but you only had data on 78 of them, well, what happened to the other 22? Like, you want to kind of know about that sort of thing. So we call that censored survival data. When you decide to censor someone from the study here, it's important to know how long they were actually in the study for during that whole point. Oftentimes what you'll find is that researchers will do the calculations with the censored data included and then without it, just to make sure things are pretty similar there, to make sure that censored data isn't really causing any particular skewing of the data whatsoever. But again, just know that if you have censored survival data, that needs to be accounted for, and we need to know like why they were censored. Was it because they dropped out of the study? Is it because they died from something else completely unrelated? What was it? So if you imagine here looking at a set of survival data, so we can see that obviously not everyone gets enrolled into the study at the exact same time. Oftentimes they have what they call enrolling inclusions, where they will basically get people in as they become available, essentially. So here they get enrolled at different time points, and then they have their ending dates. And so here you're going to find, okay, this person died in a car crash, study ended and they were still alive, or they moved, or maybe got off the protocol here. Now let's look at how we're actually going to be accounting for all these points and how we can actually graph that data out. As I mentioned, 7 patients were in the study, got included. 3 were end up being censored. And as I mentioned, one of the patients died from an unrelated cause. Now, in some studies, you'll look at death from any cause and include that. In this case here, it was considered a censored observation, but it's important that the researchers at least made note of it, right? At least you mentioned it in the manuscript. And again, looking at this patient lived for 3.67 years on the treatment. It was unknown had they been included, or had they not died in the car crash, how long they may have survived or not survived. And so oftentimes you'll find that patients will get a code here, whether they died or not, and then you'll have the actual times that they were in the study before the event actually occurred, okay? So there's a couple of different methods you can look at survival data. The most common one you're going to run into is this Kaplan Meier method, where basically you would calculate every time a patient dies within the study. And so here, basically, it's just made up of a fraction of the people who survived on a particular day. So basically divide it by the number of people who were alive at the end of the day versus the ones who were alive at the beginning of the day, okay? And it actually will account for censored patients as well there, which is very handy. And again, you're going to find that time 0 is the day that each patient entered the study, and you're going to find this can expand for years depending on the enrollment period for the study, how long it was open for. So, and again, looking at here, how you would actually graph this out. We'll show you the actual graph in a second, but in the table you would try to develop for the Kaplan Meier, you see here that time point starts at 0. Again, everyone is alive at this point here. Everyone's alive at this point, and then each time someone dies, you would calculate out, okay, well, the percentage of people that were still alive at that point there, right? And so these are the confidence intervals you're going to see. And again, here's each of those points, the number of people who are still alive. Okay, so let's look at what that graph actually looks like. So there's a few different ways of actually documenting all of this. I would tell you this is probably the most common one that you're going to run into in terms of having it show the confidence intervals in addition to actually looking at the survival curve. But notice here that each time you have someone die, they get a notch down, right? And sometimes the censored subjects get marked as like a little circle here. Here's like a little hash mark. Every time someone dies, knocks down another bunch. You know, the next time a person dies, knocks them down, knocks them down. And again, you can see the people who are censored there. And the point is that each time that happens at a certain time frame, and again, this is time 0 for everyone when they enter the study, you get this confidence interval here, the kind of the upper and the lower ranges. And so the nice thing that's beneficial though is you can actually do this with, say, 2 different treatment arms, right? Maybe you get one person, one arm that's on a certain type of chemo treatment, and then one that's on an experimental chemo treatment. And you can actually compare these curves here using the confidence intervals to find out, well, who's actually surviving for longer, which medication regimen may be better in those cases. But this is just a very frequent way of demonstrating survival curve or survival data for patients in these studies here. And again, this only can be done for things that happen a one-time sort of thing. It cannot happen more than once. Very frequently, the median survival is what's going to be used to kind of sum up the entirety of the information about one of these curves here. And so basically that's the middle value, the 50th percentile on the set of numbers, if you remember, the median. And so basically what this means is how long it takes until half of the subjects are dead. Okay, so again, if it were, say, 5 years before 50% of your subjects died, that's the median survival time. The reason why we don't look for 100% survival time is because that could take a really long time to let all your patients die off, and we don't really have the ability to do that. So what we can do is get down to that 50 percentile mark, get that median survival, and then we can start to make comparisons to that. How does this group compare on this medication treatment versus a median survival of another group? And you can actually start to do some inferential statistics on that to determine, okay, well, who's actually more likely to live longer on this treatment or this treatment? But that median survival time is very frequently used in order to account for that. Oftentimes, when you're dealing with things like cancer treatment, very frequently we'll talk about survival time in terms of 5 years. So you get a 5-year survival. Again, there's nothing special about that number. It's just more of a matter of tradition, but it's something you'll hear pretty frequently. What was the 5-year survival for this particular treatment of this kind of cancer? So what are some assumptions with survival analysis? So it should be based on pretty similar things we've seen before, that one, your sample should be random, representative of a population, right? They should be independent subjects. So again, people need to be only counted once. You cannot look at twins and things like that. And so again, you can really run into some issues if you violate any of these. It may not really be representative of your actual data there, right? Also, the entry criteria should be pretty consistent when doing these survival analyses, right? So again, because it could be years potentially between when a patient enters over that course there, you tend to find that things like diagnostic tools could change over that time period, right? And so maybe perhaps you identify a particular variant of a disease and that may affect the survival time, right? So you have to make sure everyone gets included on the same exact entry criteria. And also the endpoint should be clearly defined, right? So again, if a death gets censored, is it consistent amongst the groups you're looking at? Is it done the same way every time? You want to make sure you avoid any kind of ambiguity and just make sure it's being applied consistently throughout the study. So if someone dies from a car wreck in year 1, you still want to consider that if you censor that, and at year 10 you're still running the study, you want to censor that as well at that point if someone else died from a car wreck. And then the starting time needs to be really clearly defined there. So data analysis or data keeping is really important. So whether it's, say, the first time someone gets diagnosed with something, or it's the first hospital admission, you don't want to use something like patient recollection. Be like, hey, how long ago did you get diagnosed with hypertension? There's a lot of recall bias, they call it, where they may skew that number too early, too late, whatever the case may be there. And again, patients who die early before they've ever received whatever intervention you'd be looking at, want to at least make note of those. You don't want to just absolutely remove them because that may lead to some degree of bias there. Okay. Basically, we have what we call frequently used called the intention to treat, which basically means that even if they went off the study or they weren't included, they were lost to follow up or something like that, you still include them in the treatment group or the control group regardless. Just make sure you include all that data. That helps to reduce some of the bias you may see in some studies. And so when you're doing the censoring, that also should be made sure that that's not introducing any bias there. So for instance, if a patient drops out because they were too sick, or maybe they got cured from the disease, or maybe they didn't feel like the treatment was working, that's all related back to the disease itself. And so those patients should all still be included. If you're looking at things like myocardial death and someone dies from a car wreck, well, who's to say they didn't have MI that led to the heart, that led to the car wreck? Things like that, right? So it just needs to be consistent and should be addressed in the manuscript itself. You want to make sure that average survival doesn't change during the study. And again, this is if you're running something over a prolonged period of time. Certain things can change, like nature of disease can change. If you say, for instance, have an infectious disease that is mutating, that may make it more or less deadly. Maybe you find that the standard of care, right, has changed during the course of the study, and that is influencing the survival rate. So it's important to make sure that the treatment is consistent throughout the entire time frame, and the disease itself is consistent throughout the time frame. And so why do we look at reporting median survival time rather than mean or average survival time? We kind of mentioned this. It just takes a lot longer to finally get that the average survival time, and that would assume everyone meets that endpoint you're concerned about, versus if you have 50% of your subjects have died, that's pretty unambiguous. It's a lot easier to get in those cases there. So that's it for questions about confidence intervals and survival curves. And if you have any questions, let me know, and I'll talk to you soon. Thanks a lot. Bye.